Meow. What was that? Mr. Kitchen, Global Skill Richmondville High School of Physics. And today we're going to talk a little about the Doppler effect. And that was my representation of the Doppler effect. The Doppler effect is a change in frequency due to the relative motion of the source and the observer. The important thing is the source and the observer are getting closer to each other, or they're getting further apart. And whenever that happens, we're going to have a change in frequency that occurs. This applies to all types of waves. So we can actually apply the Doppler effect to light waves, sound waves, water waves, whatever it happens to be. Now, the way this thing really works, whenever the two objects are moving closer together, the source and the observer, you're going to observe an increase in frequency and then the decrease in frequency when they're moving away from each other. Now, as I mentioned, we get Doppler effects for all types of waves. The two most important that we talk about are sound waves and light waves. And changes in frequency for these two types of waves manifest themselves in different ways. So if we're talking about sound, sound waves will be talking about pitch, right? So we'll get a change in pitch if things are in relative motion. Where when we talk about light, the change in frequency causes a change in color. And specifically, we have two names that we use quite often for the blue shift for light, or excuse me, the Doppler shift for light. We call it a blue shift if the wavelength is decreasing and the frequency is increasing. As we said, that's what happens when things are moving closer together. And then we have a red shift. The red shift implies that the wavelength is increasing, the frequency is decreasing. Notice these things always go in opposite directions, and this occurs when the objects are moving away from each other. Now, the first example that I want to take a look at is just sort of setting things up. We don't have a Doppler effect here, but let me lean out of the shot and give you an opportunity to sketch this diagram. This represents our source of waves. Here, considering the frequency of them, they're probably sound waves, but again, this would apply to all kinds of waves. And there's a point source of these waves. Now, when you have a point source of waves, like dipping your finger into a pan of water, you're going to get circular wave fronts. And that's what I've shown here with these dashed lines. In this diagram, I really don't want to draw the entire circular wave fronts as they're expanding outward. They're not terribly important for us. All we're interested in is the part of the wave that's going into the observer's ear over here. And so I'm just showing the wave fronts, a few representative wave fronts over here, and a few representative wave fronts on this side. So we have two observers over here. We're producing sound waves of 100 hertz. This symbol is F sub 0, or as we often say in physics, F naught. It represents the original frequency. And then we have F prime over here. This is what the observer hears, and we have another F prime over here. But the point is they're all the same. There's no motion in this, so it's just as you'd expect. If you're producing 100 hertz sound over here, the observers are going to pick up 100 hertz sound in any direction. Now, when we get to a Doppler shift, we need to set this source of waves in motion. Right, and that's what I'm representing up here. Here's my circular source of waves once again, and the waves are moving to the right, or the source of waves is moving to the right with some velocity v. Now what happens is the waves get squeezed together over here on this side. We end up with a small wavelength, and the waves actually get stretched apart over here on the back side, and we get a longer wavelength. I'll be demonstrating this to you in class. We're still producing the original frequency, or F naught is 100 hertz. But over here on the right-hand side where these waves are squeezed together, the frequency is higher. Now we can see wavelength, it's hard to see frequency, but think about it this way. If the waves are coming in and they're all packed close together, the frequency is the number of waves that you get per second. And what you're going to get is the waves are coming in rapidly, one after another, boom, 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 where we get a high frequency. So although we can see wavelength, large frequencies and short wavelengths always go together. Now, you'll note I've adopted this convention where I'm showing short wavelengths in blue and longer wavelengths in red. This is often done due to the Doppler shift for light. The short wavelengths are toward the blue end of the spectrum, and the red wavelengths are toward the longer wavelength end of the spectrum. Okay, so we have longer waves over here, we have short waves over here. I've kind of separated this into two. Now, whether these are sound waves in air, light waves in a vacuum, it doesn't really matter. The velocity of the wave will be constant in that given medium. But what we have over here on the red-shifted side, or the longer wavelength side, where the source is moving away from the observer, we have a constant velocity. We end up with a longer or larger wavelength. So I'm using this exaggerated symbol notation. Put a big lambda over here and a small frequency. These two multiplied together still have to give you the same value of velocity that you would get anyway. So what we end up with, well, is a longer wavelength, which gives us a lower frequency. We always talk about frequency for the Doppler effect. If this is sound, this would be a lower pitch. Or if it's light, we would call this a redshift, because the waves are shifted toward the red end of the spectrum. They're not necessarily going to be red, but shifted toward that end of the spectrum. And then the opposite thing is happening over here. What we have is a constant velocity, but make a large f and a smaller lambda. We have a high frequency and a small wavelength. Higher frequency is going to lead us to a higher pitch if we're talking about sound, or if we're talking about light, we're going to call this a blue shift. Again, the waves aren't necessarily blue, but they're shifted toward the blue end of the spectrum. And finally, I want to give you some examples of the Doppler effect. One of the most pronounced examples that you'll hear is if you ever watch racing on TV, especially the Indy cars or the Formula One cars. When those cars are moving at very high speed, the waves get squeezed together in front of the car, it gets stretched out behind the car, and you literally hear this meow as the car goes by the observer over here. The Doppler effect is that change in pitch from ee to ow as the car goes by. And the faster the car goes, of course, the greater the Doppler effect, the Doppler shift is going to be. Another example would be a train whistle. If a train is going by and it's sounding its whistle, you'll hear an artificially high pitch as it's moving toward you and a lower pitch as it moves away. Doppler radar is something that all the meteorologists in the area are now using. Regular radar just sends out microwaves, about the same frequency as we use in a microwave oven, and it sends those waves out and waits for them to come back. We measure the amount of time out and back, and because we know the velocity of microwaves, we can figure out how far away the reflecting objects are. Well, that was the original radar. Now the new Doppler radars send out waves, microwaves again, of a known frequency, and they measure the frequency of the waves coming back. That way, if something's moving away from you, we're going to get a lower frequency coming back, and you can calculate the velocity of that object. The opposite is true of a higher frequency. And usually on the Doppler radars that they show you on TV, they're going to use this red and blue to represent, well, blue is something moving toward you, and red moving something away. We have red shift of all the stars, and I point out this is good evidence of the Big Bang Theory, not the TV show, but the Big Bang Theory of the beginning of our universe. No matter where we look in the sky, we look at all the stars, and we know what the spectrum of light from those stars should look like. The light from stars is composed primarily of the spectrum of hydrogen and helium, the most common elements that make up the stars. And what we see is the pattern spacing is the same, but everything is shifted toward the red end of the spectrum. All the spectral lines are shifted toward the red end of the spectrum. And from that, we can calculate that, well, first of all, we can tell that the stars are all moving away from us, but we can also calculate how fast they're moving away. And the farther away they are, the faster they're moving. So what we believe is, since all the stars surrounding us are moving away from us, that we actually live in a universe that's somewhat like a bubble that's expanding, and as it expands, it drags space and time with it. Space and time literally are expanding as well. And the last thing, and I'll show you an example of this in class, is the sonic boom. When aircraft approach the speed of sound, we call that the sound barrier, and when they go faster than the speed of sound, they continuously produce this large amplitude sound. This almost sounds like an explosion, and we call that a sonic boom. So I'll give you some more examples of this as we pick it up in class.